Before we begin with calculations and examples, let us quickly do a recap of packing in crystalline solids. We will focus on only three types of unit cells. We will focus on primitive cubic lattice, which in some textbooks you will see written as simple cubic structure, or SCC. The feature of primitive cubic lattice is that the lattice points is at the corners of a cube, all the 8 corners of a cube. We also will talk about body-centered cubic lattice. In body-centered cubic lattice, you also have the 8 lattice points in the corners, but you have an entire atom in the center of the cube. And we will also talk about face-centered cubic lattice. The feature of face-centered cubic lattice is that it has the 8 lattice points in the corners, but it also has 6 lattice points on each of the faces of a cube. Remember, a cube has only 6 faces. Body-centered cubic lattice is also called BCC, while face-centered cubic lattice is also called FCC. The diagram here shows you how the atoms are stacked together to showcase each unit cell. But if you look at these structures properly, you will see that the atoms are not completely inside the cube. Some parts of the atoms are outside the cube. Let us now take a look at how to calculate the net amount of atom in a unit cell. Let us begin with the primitive cubic structure. In primitive cubic structure, you remember that the atoms are only in the 8 corners of a cube. Now, each corner of a unit cell is shared by 8 other unit cells, which means that the net number of atoms in a primitive cubic structure will be 1/8 times 8, and that works out to 1 atom for SCC. So we only have 1 net atom per unit cell in primitive cubic structure. Let us now take a look at body-centered cubic structure. In body-centered cubic structure, we also have 8 atoms in the corners, and that works out to 1/8 times 8, which is 1 atom. But we have an entire atom in the center of the cube. That is a whole atom, which means that the total number of atoms in a BCC unit cell would be 2. In face-centered cubic structure, we have 8 atoms in the 8 corners, That will be 1 over 8 times 8. We also have 6 atoms in each of the 6 faces of the cube. And each face of a unit cell is shared by 2 unit cells, which means that the total number of atoms from the faces would be 1 over 2 times 6, which will work out to 3. That means the net atoms per unit cell for FCC will be 4 atoms. Please remember these numbers. There is one more atom location that we have not mentioned here, and that will be the edge. The edge will be this side. And in a cube, we have 12 edges. And each edge is shared by 4 unit cells. The slide on the screen right now is one of the most important slides when you're talking about unit cells. It summarizes most of the information you need to know. As you can see from the slide, SCC has a total of 1 atom per unit cell. And if you can look at the structure properly, you will see that the 8 atoms are only stacked in the 8 corners of a cube. The coordination number is 6, which means that each atom has 6 nearest neighboring atoms. But this is another very important terminology to remember. The edge length of each unit cell in terms of the radius of the atoms. The calculations for this would not be shown in this video, but I need you to know that for each cube, the length of the edge is related to the radius of the atoms that make up the unit cell. Please remember these relationships. Let us work on this example together. A metal nitride has a nitrogen atom at each corner of a unit cell. Let us try to calculate that. Nitrogen atom at each of the 8 corners in a unit cell. Since each corner in a unit cell is shared by 8 unit cells, that means the total nitrogen atoms in one unit cell will be equal to 1 over 8 times 8. And that will be equal to 1. The question goes forward. And a metal atom at each edge. A metal atom at each of the 12 edges in a unit cell. That means the total number of the metal atoms in the unit cell will be equal to 1 over 4 times 12. Why 1 over 4? The reason is because each edge of a unit cell is shared by 4 unit cells. So 4 will cancel out 12 to get 3 metal atoms. Now the question says we should write the empirical formula for this metal nitride. We have 3 metal atoms and we have 1 nitrogen atom. That will be the empirical formula. And which of these options will be correct? That will be B. Remember, barium, sodium, aluminum, and titanium are metals, but only option B is similar to the empirical formula that we got. Let us now take a look at this next problem. Palladium, element number 46 on the periodic table, is named after the asteroid Pallas. Both were discovered in the early 1800s. Pallas is probably the second largest main belt asteroid in terms of volume. Okay? If the radius of palladium is 0.138 nanometers, now that is a very important information, and it crystallizes in a FCC arrangement, that is another powerful information. What is the volume of a unit cell of palladium in cubic centimeters? Now, we want to find the volume. The volume of a unit cell will be equal to the length of an edge of the cubic cell to the power of 3. Why is that the case? The reason is because a unit cell is a cube, and the volume of a cube is one side of the cube raised to power 3. So, to solve this problem, all we need to do is to find the length of an edge of the unit cell. How do we find it? If you remember from this slide, we related the length of the edge of a unit cell to the radius of the atoms that make up the unit cell. In the case of FCC arrangement, the length is equal to 2 root 2 multiplied by r, as you can see here. Therefore, the length of the edge of the FCC arrangement will be equal to 2 square root of 2 multiplied by r. We know the radius of palladium, so we just plug it in, which means that the length of an edge of the unit cell will be 2 root 2 multiplied by 0.138 times 10 to power negative 9 meters. Why 10 to negative 9? We have nanometers, and nano means 10 to negative 9. If you put these numbers into your calculator, you should get L equals to 3.9032229 times 10 to negative 10 meters. Therefore, the volume will be equal to 3.903229 times 10 to negative 10 meters to power 3. If you put this into your calculator, you should get 5.9466 times 10 to negative 29 cubic meters, which we can then convert to cubic centimeters as the question requests. If we multiply this by 10 to negative 2 meters equals to 1 centimeter, everything to power 3. Why is it 10 to negative 2 meters? Because centi literally means 10 to negative 2. So, if you plug this into your calculator and you round to 3 significant figures, you should get 5.95 times 10 to negative 23 cubic centimeter.